The National Electrical Code Section 250.53 states that where the resistance to ground of any driven rod electrode is greater than 25 ohms, a supplemental electrode or electrodes shall be installed in accordance with 250.53 ATWA. The Institute of Electrical and Electronics Engineers Standard 142-2017, also known as the IEEE Green Book, Section 5.59 states that if the ground resistance of a single electrode cannot be reduced to 25 ohms or less by the usual method, a second ground electrode should be added or other action should be taken as described in Sections 5.59.1 through 5.59.3. The intent of these code requirements is to ensure that the grounding system has a low resistance to ground, which is essential for the proper operation of electrical equipment and for the protection of personnel. When the resistance to ground of a single electrode, for example, a ground rod, exceeds 25 ohms, the addition of a supplemental electrode, such as a cold water pipe, can help to reduce the overall resistance of the grounding system. In cases where the ground rod resistance is greater than 25 ohms, the NEC requires a third grounding electrode. The IEEE Green Book provides guidance on alternative actions that may be taken, such as installing additional ground rods or improving the connection to the cold water pipe. The formal documentation supports the requirement for a third grounding electrode when the ground rod resistance is greater than 25 ohms. This requirement is intended to ensure a low-resistance grounding system for electrical safety. Grounding electrodes are essential components of an electrical system, providing a path for fault current to return to the source, thereby tripping over current protection devices like circuit breakers or fuses. This protective action minimizes the risk of electrical shock and equipment damage. The NEC and IEEE standards emphasize the importance of a low-resistance grounding system to facilitate this rapid fault clearing. A grounding electrode system typically consists of one or more grounding electrodes bonded together to form a network that provides a connection to the earth. Common types of grounding electrodes include ground rods, ground plates, underground metallic water pipes, and concrete-encased electrodes, also known as U for grounds. The selection and installation of grounding electrodes must comply with specific requirements outlined in the NEC and other applicable standards. The 25 ohm resistance threshold specified in NEC section 250.53 is a critical benchmark for evaluating the effectiveness of a single grounding electrode, typically a ground rod. If the measured resistance to ground exceeds this value, it indicates that the electrode is not providing an adequate low impedance path for fault current. Several factors can contribute to high ground rod resistance, including soil resistivity, electrode depth, and electrode diameter. Soil resistivity is the measure of how well the soil conducts electricity, and it varies depending on factors such as soil composition, moisture content, and temperature. High soil resistivity can significantly impede the flow of current through the ground, increasing the overall resistance of the grounding system. To mitigate the effects of high soil resistivity, various techniques can be employed, such as driving the ground rod deeper into the earth, using multiple ground rods spaced apart, or treating the soil with conductive materials to improve its conductivity. The depth and diameter of the ground rod also affect its resistance to ground. Generally, longer and thicker ground rods provide a larger contact area with the soil, resulting in lower resistance. However, there are practical limits to how deep and thick a ground rod can be, and other factors, such as soil conditions and installation constraints, must also be considered. When a single ground rod fails to meet the 25 ohm resistance requirement, the NEC mandates the installation of a supplemental electrode. This supplemental electrode is intended to work in conjunction with the original ground rod to reduce the overall resistance of the grounding system. The supplemental electrode can be another ground rod, a ground plate, a metallic water pipe, or any other type of grounding electrode permitted by the NEC. The choice of supplemental electrode will depend on site-specific conditions and the availability of suitable grounding mediums. The IEEE Green Book provides additional guidance on selecting and installing supplemental electrodes. It recommends considering factors such as the type of soil, the proximity of other underground utilities, and the potential for corrosion. The Green Book also suggests alternative actions that may be taken to improve the grounding system, such as enhancing the connection to the cold water pipe or installing a ground ring encircling the building. Improving the connection to the cold water pipe involves ensuring that the bonding jumper between the grounding electrode conductor and the water pipe is properly sized and securely connected. The bonding jumper should be made of copper or other corrosion-resistant material and should be protected from physical damage. A ground ring is a continuous loop of bare copper conductor buried in the earth around the perimeter of a building or structure. It provides a low impedance path for fault current and helps to equalize the potential between different parts of the grounding system. Ground rings are commonly used in large industrial facilities and data centers where a robust grounding system is essential. In addition to the NEC and IEEE standards, other industry standards and best practices provide guidance on grounding system design and installation. These resources can help engineers and electricians ensure that grounding systems are safe, reliable, and compliant with applicable regulations. Regular testing and maintenance of grounding systems are essential to verify their continued effectiveness. Ground resistance measurement should be performed periodically to identify any degradation in the performance of the grounding electrodes. If the resistance exceeds acceptable limits, corrective action should be taken to restore the grounding system to its original condition. Grounding is a fundamental aspect of electrical safety, and a properly designed and installed grounding system is essential for protecting people and equipment from electrical hazards. Adherence to the NEC, IEEE standards, and other applicable guidelines is crucial for ensuring that grounding systems meet the required performance criteria. Furthermore, understanding soil composition, moisture content, and temperature of ground rods affects the resistance of the rods and the electrical conductivity. The grounding electrode conductor, or GEC, connects the grounding electrode to the electrical system's grounded conductor, typically the neutral bus in the service panel. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. It is crucial to use the correct size GEC to ensure that it can safely carry fault current back to the source. The equipment grounding conductor, or EG, provides a path for fault current from electrical equipment back to the service panel. The EGC is typically a wire, conduit, or other metallic raceway that is connected to the equipment enclosure and to the grounding bus in a panel. The size of the EGC is determined by the size of the overcurrent protection device protecting the circuit, as specified in NEC Table 250.122. Proper bonding is essential for creating a low impedance path for fault current. Bonding involves connecting all metallic parts of the electrical system together, including equipment enclosures, conduit, and metallic water pipes. Bonding jumpers are used to connect these metallic parts together and should be sized according to NEC Table 250.102. Surge protection devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning or other transient events. SPD are typically installed at the service entrance and at sensitive electronic equipment. They divert surge current to ground, preventing it from damaging equipment. Regular inspection and testing of grounding systems are essential to ensure their continued effectiveness. Visual inspections should be performed to check for any signs of corrosion, damage, or loose connections. Ground resistance testing should be performed periodically to verify that the grounding electrodes are still providing a low impedance path to ground. The fall of potential method is a common method for measuring ground resistance. This method involves driving two auxiliary ground rods into the earth and measuring the voltage drop and current flow between the grounding electrode and the auxiliary electrodes. The ground resistance can then be calculated using Ohm's law. Soil resistivity testing is another important aspect of grounding system design. Soil resistivity measurements are used to determine the conductivity of the soil and to select the appropriate type and size of grounding electrodes. Soil resistivity is typically measured using a 4-point test method, which involves driving 4 electrodes into the earth and measuring the resistance between them. Electrolytic ground rods are a type of grounding electrode that is designed to improve the performance of grounding systems in areas with high soil resistivity. Electrolytic ground rods contain a chemical compound that leaches into the soil, improving its conductivity and reducing the ground resistance. Concrete encased electrodes, also known as UFA grounds, are grounding electrodes that are encased in concrete. UFA grounds are typically used in new construction and can provide a very low resistance connection to ground. The concrete helps to protect the electrode from corrosion and provides a stable grounding environment. Grounding and bonding are critical aspects of electrical safety. A properly designed and installed grounding system can protect people and equipment from electrical shock and equipment damage. It is essential to follow the NEC, IEEE Standards, and other applicable guidelines when designing and installing grounding systems. In summary, the NEC and IEEE Standards emphasize the importance of maintaining a low-resistance grounding system for electrical safety. When a single ground rod exceeds 25 ohms, supplemental electrodes are required to reduce the overall resistance. Regular testing and maintenance are essential to ensure the continued effectiveness of grounding systems. In cases where a ground rod exhibits a resistance greater than 25 ohms, the addition of a third grounding electrode serves to create a more robust and reliable path to ground. This redundancy is particularly important in environments where soil conditions may vary or where there is a higher risk of corrosion or damage to the grounding electrodes. By installing multiple grounding electrodes, the overall impedance of the grounding system is reduced, which enhances its ability to quickly and effectively dissipate fault currents. The third electrode acts as a backup, ensuring that there is always a low resistance path available, even if one of the other electrodes becomes compromised. The spacing between grounding electrodes is also an important consideration. Electrodes should be spaced at least the length of the longest electrode apart to avoid overlapping spheres of influence. Overlapping spheres of influence can reduce the effectiveness of the grounding system by concentrating the current flow in a small area. By spacing the electrodes properly, the current is distributed more evenly throughout the soil, which reduces the overall resistance and improves the performance of the grounding system. The type of soil also plays a significant role in the performance of grounding electrodes. Different types of soil have different resistivities, which affect their ability to conduct electricity. Sandy soils tend to have higher resistivities than clay soils, which means that they are less conductive. In areas with sandy soils, it may be necessary to install more grounding electrodes or to use special techniques to improve the conductivity of the soil. Soil conditioning is a process that involves adding chemicals to the soil to improve its conductivity. This can be an effective way to reduce the resistance of grounding electrodes in areas with high soil resistivity. However, it is important to use soil conditioning products that are environmentally friendly and that will not damage the surrounding soil or groundwater. The connection between the grounding electrode and the grounding conductor is also critical. The connection must be mechanically sound and electrically conductive to ensure that fault currents can flow freely through the grounding system. Connections should be made using approved connectors and should be protected from corrosion. The use of exothermic welding is often recommended for making grounding connections, as it provides a permanent and reliable connection that will not loosen or corrode over time. The grounding electrode conductor, or GEC, is the conductor that connects the grounding electrode to the electrical system. The GEC must be sized appropriately to carry the maximum fault current that is likely to occur. The size of the GEC is determined by the size of the service entrance conductors, as specified in NEC Table 250.66. The GEC must be installed in a manner that protects it from physical damage. The grounding system should be designed to minimize the risk of ground loops. Ground loops occur when there are multiple paths to ground, which can create circulating currents that can interfere with sensitive electronic equipment. Ground loops can be avoided by using a single-point grounding system, in which all grounding conductors are connected to a common grounding point. Surge protection devices, or SPDs, are an important part of a comprehensive grounding system. SPD protect electrical equipment from voltage surges caused by lightning or other transient events. SPD should be installed at the service entrance and at sensitive electronic equipment. The NEC requires that SPD be properly grounded to ensure that they can effectively divert surge currents to ground. Regular testing and maintenance of the grounding system are essential to ensure that it continues to function properly. Ground resistance measurements should be performed periodically to verify that the grounding electrodes are still providing a low resistance path to ground. Visual inspections should be performed to check for any signs of corrosion, damage, or loose connections. Any problems that are identified during testing or inspection should be corrected promptly. The information provided here is intended for general guidance only and should not be considered a substitute for professional engineering advice. A qualified electrical engineer should be consulted to design and install a grounding system that meets the specific needs of each application. In conclusion, when a ground rod resistance exceeds 25 ohms, the NEC and IEEE standards require the installation of supplemental electrodes to ensure a low-resistance grounding system for electrical safety. This requirement is intended to protect people and equipment from electrical shock and equipment damage. Regular testing and maintenance of grounding systems are essential to verify their continued effectiveness.